Hello YouTubers, today we're going to be discussing this turbine that I put together here. It's a small tiny turbine. Let's see the dimension are right here. Let's touch here better, and basically the internal diameter is about 55, pretty much close to the size of this impeller or rotor. The outside 65. This is the inlet, it's about, I think it's 8 millimeters, I believe, 8 millimeters, and that lead, that flow go into this cavity just to allow the turbine to rotate so you can extract power out of it. I haven't put a chap into it because I'm more interested on the CFD simulation than anything else. So how about that was about right there, about 14. So the internal diameter is 14, larger this side that the inlet, which is about 8 millimeters. So basically this is going to be run with water. Again, it's a small turbine. I don't expect obviously to power the house with this, and the flow rate is a tiny flow rate. It's about 1.5 gallons per minute getting in at the at the aqueduct pressure, which that will be about, I don't know, 40 psi. So 40 psi getting in and moving the turbine, and the question is how much energy can you extract out of it. And the flow rate again is 1.5 GPM. So that's the main idea. So this was made on everything was created in Solidworks. I already did some preliminary study on CFD. As you can see, there are more parts here that, for example, lead 1 and lead 2 are to close these, or these that go here. For example, if I take this out, I'm gonna add it at a later time. You see that kind of seal, it's a plug there just to do internal simulations. So that's another plug here. But the main part here of this is the rotor and the casing, the general casing, as you can see. And I add also a casing lead that's right now is transparent, so you can see through it. And there's something else here very important. It's kind of let's see, it's called here that rotating body. You can see that is something like you create a body to enclose what is going to be rotating, and that's very important. And sometimes if you are new to SolidWorks, kind of hard to understand this part of flow simulation, because basically within that rotating body you put whatever is going to be rotating, so at a later time you will see it moving and it start to make sense. But again, it's something that you create a solid to enclose in this case the rotor, and it's pretty much slightly bit larger than the size of the impeller, but enclose everything that is going to move from this part up to this part, which is also part of the in this case of the propeller. Actually, let me get this housing, that's the casing here. Let me get the casing out for a second so you see what I'm saying. And that's basically everything that is within this rotating body. See, that's the rotating body. Right now it's transparent, so you can see it, so we can see the impeller, and you also see here the inlet, and this is the outlet. So that's basically the main point. Now what I'm gonna do now is move all these but into assembling, because I did it directly from here. You can do it, from here directly you can go to flow simulation and you can do it, but I want to do it first through the assembling part, and then from assembling then you move to flow simulation. Because one of the things that you could certainly do in assembling is move this, put this in a different start position for your simulation. Right now it is the way it is. If I do flow simulation, I will start to do it the way it is right now. Like for example, if this is going to be at 0 RPM in one point in time, which will provide the maximum torque, the kind of a holding torque that is required for this not to move as water get in at 40 psi and the water is rushed out this way. So that would be the maximum holding torque. So for calculation, but as soon as they start to spin, the extraction of torque get diminished. So let's go back to let's do here. Let's get the casing back again. Now, one thing for sure is that you have to take all this part and make like this, like go here and then do an insert into new part. So every part here that you really want to go into assembling, you got to do that, like the turbine rotor, the casing lead, the casing, and the rotating body. So those are the 4 things that you really need. Lead 1 and lead 2 are created on the spot when you move to flow simulation, so you don't need it. Again, like for example, I already did this, but that's the main idea. So you will lose something like this, and it's gonna call turbine rotor. If I hit here, then it will show up. Then I say yes, and that's the new part. Since it's already here, I will cancel. Gonna bail out from here and close this. I don't need this. And from now, I'm gonna go to here. It's gonna make assembly from new part. We're gonna make a new assembly. We say okay. All right. So here's the casing. That's the thing that I need. And so I'm gonna put that back there, and it's fixed. It's fixed. Can move it around, so that's good. So now we need the rotor, so we go back again and we insert component, we browse. It's not here, although let's see, browse. Let's add a turbine. Here we go. The turbine rotating body, open. Now, before putting that there, let's do this. First thing that I want to do is this guy and this guy, holding control. Now you want them to be concentric, and now the next part is that this part here and this part here, they want the bottom heat control, that bottom there's a distance. You want a distance there, and that distance is about 2 millimeters. That's the clearance between the rotor and the bottom of the casing. So we accept that. There we go. Now the nice thing is that you can move this around. See, that's what I was saying, that you can have it like right here. What happened if this is right there? You see, it will start to turn around, you know, but that's a different start than when you leave it here. So that's the advantage of going from to assembling. Now the next thing is I need to put the lead on it, and we are pretty much done. We have this looking good. Now let's see if I can get a view this way while this is rotating. Yep, you can see it right there. And this side, which is smaller because I say inlet, let's get a little bit more. There we go. So that's how this will go. Now let's put the lid on it, and so insert component and browse because it's not there. The best thing is that you prepare sort of like a folder where you have everything there, because sometimes you start to do some revisions on it and it will create a mess. So this is the lid, open, and we are right there. Now the only thing that I need to do is get that guy. This guy is gonna be concentric with this guy, and the next part is that this surface gotta be touching this surface. So, and we want them to be Sorry for this. We want them to be touching like this. There we go. Now obviously you don't see the turbine, but what we're gonna do now is step here and do change transparency, and there we go. So you have it right there. And the story is that from here we probably want to go to flow simulation, which is what we're gonna do. And we're gonna save this. We're gonna save it. Save all. Reveal. And this assembler is gonna be called water turbine. And this is very small sizes. I don't expect more than 5 watts at the most. In fact, I don't even get close to maybe to 1 watt. That's what I'm saying. Water turbine, let's save. And that's basically it. We are ready now to do the flow simulation. Let's see, from here we go flow simulation. We're gonna go to a wizard. Start this project. It's gonna be called water turbine. Well, let's put a turbine, water flow turbine, water flow turbine, water flow turbine. Next. Now, what we're gonna use here? It's always kind of a messy. Let's see. We want the velocity. I don't have problem. Pressure, I'm gonna be using PSI. I'm more familiar with PSI, pound per square inch. That will do. Now load and motions. Let's see here. The angular velocity is RPM. That's what we typically use, RPM. So we have RPM and we have pounds per inch square or PSI. Anything else that I would like to change? The flow rate, definitely flow rate, volume flow rate, meter cube per second. I said 1.5, but I said gallons per minute, so we want to change that to gallons per minute, gallon per minute. I got here UK, US. There we go. Got in US, so we got that. Next, it's gonna be internal. We're gonna exclude cavities without flow conditions, yes. And here's a big deal. This is where the problems start. What we're gonna do? We're gonna have a rotation, but the type. If you haven't done this, sliding, and that's a very important note there. Consider time dependent analysis. We're just gonna say okay, and it hit it right here. I put the time dependent, and it says you the analysis, total analysis time. I can change that later on, but I'm gonna leave it the way it is right now. But it's good enough, so we know what's going on there. And sliding, it's extremely important that you have this in sliding mode, because the way this is gonna work is very different when it's CDs left versus when it's CDs. So unless this goes extremely fast, averaging will be very bad and very poor results, like don't make any sense. So we're gonna use sliding, the concept of sliding, and you will see later on that it makes a lot of sense. So I don't think that we have to do anything else here. Next, now it's going to be water. So see, water is the last one right here, add. Now next, we're not gonna touch this. We're gonna leave that the way it is. Now here, the only thing that I'm gonna change the coordinate system, as you can see, is on the X, but actually this is rotating on the Z. So I'm gonna change this to Z, and we say OK, and I think that nothing else to change. We finish. We leave my friend do all the trick. Now here is the one important thing. It kind of knows that I'm gonna be doing internal. Well, actually, I said internal. For internal, it doesn't recognize properly a closed volume. So, as I said here, is an internal task must have a sealed internal volume. You need to close opening and hold to make the internal volume seal. You can close opening with creativity tool. You want, let's say yes. Now, what are they? Well, right here is one. You see, you touch a surface or a face that can be plugged like this, and it plug it. And how about the other side? Again, touch here, it's plugged, and that's perfect. And the nice thing is that it also recognizes the size of the the mesh eventually that we're gonna be analyzing. Recognize from this up to here, so that everything there will be analyzed, but more important, what is happening here in this area, in this region. So I will say that looks good. I'm gonna accept that, and yes, say yes, say yes. So now everything has been properly set, and basically we are only let's see what else we need to do. First thing that I might try to do is go here to the rotating region. So we're gonna insert a rotating region, and what actually there's a problem here. Let's see what is the problem. I have 3 bodies, but there's one missing. The rotating region is totally missing. So let's stop here for a second, and let's go back to here, and I need something here, and I'm not sure whether this is gonna be updated or not, but I'm missing the rotating region because I have the casing, the lead, and the rotor, but not the rotating region. And that means that I need to go back here and assembly and insert a component and look for it. Browse, and we're gonna browse, and that's gonna be rotating body. That has not been changed. That's okay. Front, I can use that one. Open. And here's the issue. That thing there need to completely surround this guy, and to do that, the first thing that I want to do is, let's try the concentric part here. That part with could be this part here. There we go. Now, yes, I know. And so now this gotta go in until you see how you happen to see there. That means that is beyond where it should be. So you want to take that guy out and just barely close, so that now one thing that I could certainly do is I might want to ensure that the internal distance, let's see if I can get that the internal distance, remember, of this is going to be hard, but the internal distance, I wanted this to be right in the middle. So I remember this right. I'm gonna do like a 1 millimeter distance between this here, that there. Let's see if I can do it this way. That distance there. What should that be? 1 millimeter. Let's see if I can get that right. 1 millimeter. There we go. Let's say yes. And there we go. So look good. Shouldn't be. In fact, if I take this one off, let's take this one off. That's let's see which one is this one. That's the casing. We're gonna get that. There we go. And let's check. It look good. That look good. All right. Now we have enclosed our rotor, so we can take this out. Let's see. And now I want to see what's going on behind. There we go. So I have my body, my rotating region properly set. Now I think this looks better. Now let's upgrade all these. So, and now let's see if that kind of percolate into what I was doing, which was the flow simulation part. Let's see. Let's go back here and let's see if I have a rotating region that I can insert now. Yes, it's right there. Now I can pick it. There we go. See, rotating body. Excellent. Now it's turning on the wrong direction. Should be clockwise. That means that I will be dealing with negative value here. Now let's put let's start with a negative 50 RPM. What that mean? Why negative? Because I know that due to the position of the impeller, this has to turn clockwise. Counterclockwise is just the way it presented to me, but it has to be this way. So a negative torque, it only means that it's moving, is the amount of energy that you are extracting from the turbine. Now if that torque for any reason became positive, it means that this is turning faster than is allowed because of water flow. You see, like for example, if I put negative 1000 and there's a positive torque, mean that the water is resisting that the RPM that I'm imposing to the system. It cannot turn that fast unless you impose energy. So as long as the torque is negative, it just means that you're extracting energy. I mean, like for example, if you put like 0 RPM here, that means that's the maximum amount of energy that you might extract is from this impeller not moving at all, because it's, you are holding it in place, and that would be maximum torque. As you start to move, the torque will get smaller and smaller. You're gonna get to a point, like for example, I don't know, maybe 500 RPM or 600 RPM, that you are not extracting torque at all. So like it's moving kind of a free spinning at the pressure drop that you get from this point to this point, and that's the torque that you're extracting multiplied by the RPM. And if torque is 0, obviously you are not extracting energy. So that's why the torque has to be cannot be 0. It has to be a negative value. But how negative? The higher the better. But this is a tiny turbine, so you're gonna get, I don't know, very small value. So now I put negative 50 RPM and anything else here. And that's why I put RPM, because otherwise you will be working with rad per second or so, something like that. So that's looking good. So we accept that. We accept OK. Now, boundary conditions. The boundary conditions will be, we're going to insert a boundary condition, and that will be on this phase, the internal phase, this one here. That one is where I know the pressure. That's what I know, static pressure. And this will be basic 1 atmosphere, but that will be about 40 psi. Could be higher, could be less. That's water from your local water supply system, which is typically about 30 to 40 psi. That's getting in. And what else I need there? I think that we are good enough there. We're gonna accept that the way it is. Now, how about another? I need another boundary condition, which will be again on this internal phase, and that will be outlet flow rate, and that's 1.5 gallon. That's typical. Could be up to 2, but again, depending on your water supply, I've seen 1.5 to 2 GPM typically. Now, here's a couple of things that kind of caveat here. Relative to rotating frame, actually, no, absolute. That's another. That's should be absolute. We want to be careful with that. How about other goals? In other goals, I always would like to know. This is kind of tiny here. I don't see what's going on. How about static pressure? All right, that's a goal there. So I want to know what's the pressure drop between the 40 versus what's the pressure here, and that's good for calculating the efficiency of the system. And so look good. So we're gonna say that. I think nothing else here. We're gonna accept. Yes. Now let me double check on this one. Edit definition. You know, sometimes it make kind of weird references. You see, this is not good. Pressure potential rotation. I don't know where that comes from. No, not at all. That's pressure, absolute pressure, and that's it. Nothing about rotation or anything like that. Be careful. Again, I mean, are the kind of things that make this kind of all of this complicated. This type of analysis. Those are little details that I'm showing you here, and we accept that, and I think that we are getting better now. Now, I always like to see the let's see, anything else here? Yeah, I'm going slow. I have a computational domain. That's okay. That's perfect. Nothing to change there. The fluid domain, I'm only working with one fluid domain, which is just water. Not a big deal. Rotating region, I identified that already. Right there. It showed me the RPMs, and put the two conditions. How about the goals? Well, on the goals, I definitely, now here it's gonna be a problem because I don't see the turbine, and or the rotor. So let's go back for a second into assembly, and let's go back and let's see. I got the turbine rotating body here. Let's get that on this so I can see let's see if I can pick the turbine, the rotor. Yes, I think I can certainly do that. All right, so now it looks good. Now let's regenerate this time to time just to be sure everything looking good. Let's move now here, and there we go. So now let's go back and add another goal here, which is the torque, and that's going to be a surface goal. So So now you see it. So I'm gonna pick that all from here. Let's see, turbine rotor, the turbine, and I pick all the part together. So I got the torque right there, and I'm gonna pick the torque. The one that I'm interested is on the Z direction. So we move here to here, torque in Z, and that will do. So we accept that. We got that. We got the pressure for the pressure drop, and now the mesh. Let's see. Global mesh is gonna be. We're gonna leave that there. I'm not gonna mess with that. So, but one thing that I learned is on this region inside, we gotta do something there. Let's see. Insert local mesh, and the local mesh will be within the rotating body. So that's where you want to have a different side, kind of a more. The more you add here, this is going to take forever. So you want to be careful here what you do. And so I'm going to leave that there on 2, and we're going to accept that. And now we're going to run this. Let's see, mesh, create mesh, run. Open that up, and let's see what it come out. About 49,000. That's no bad. That's no bad. Mesh. Insert that mesh so we see it. There we go. Okay, now we accept that, and there we go. So now you know how tiny they are, and they will work out okay. Compare those with the regular mesh, the global mesh, right there. See, huge mesh versus the tiny ones within the rotating body. Well, we are getting there. Anything else now? We need to go one more step. It has to do with go back here. Let's see, flow simulation. We need to go to solve, calculation, control options, and everything looks good. Physical time, actually you have to, like for example, 1 I only care about time. 1 second is more than enough. Believe me, this is gonna take forever, because basically I'm gonna do a very small step. Let's see, that's okay there. Refinement, that's good. Solving, here's the issue. I can leave that in auto, but gonna leave that in manual. Obviously cannot be 1 second, that's way too big for this, so it's gonna be very small, 0.002 of a second. All right, so now what we're gonna do here, that I don't touch anything of that, but then it's gonna be periodic, and I'm gonna leave that the way it is, except that this here I'm gonna save everything on the main in case I need it. So we said okay, and going back again, solving. It's gonna be on time. That's what it's gonna be, dynamic 0.02 the step. Refinement, looking good, nothing there. Finishing 1 second, the physical time. So that's the idea. The idea is that this will stop when you hit 1 second of that. And so we said okay. If I screwed up, then I check again. my parameters and see how this looks like. But looks like again that everything looks good. I mean, I'm moving from I create the old part in SolidWorks parts, move to assembling, and from assembling move to flow simulation. Last time I moved from solid part to flow simulation. I don't know. Again, I don't know. It's up to you. So it looks good there. Now, what I'm gonna do now is let's see. I already run this and it runs okay. So let's run. Let's figure out what's gonna happen. I already did the mesh. It's gonna be a new calculation. So I'm gonna use this computer. Use all core. 8 cores. If I have 16, even better. Load result. Run. So now let's go here. That's being generated, and let's go quickly here. Let's put all of them, and let's say okay. But now use as soon as you get this pop, there we go. As soon as that pop, now this is the story from playing. You wanna this is about, let's see, I would say 0.015 of a meter. Let's see, auto min max, yeah, settings, whatever, 6 up, definition. Something's not right. Maybe it's not sliding. I see some weird number here. I don't know where that comes from. And so let's say okay. And kind of weird pressure, meaning that probably have something wrong that I need to check. Very weird pressure. It's rotating. Let me stop and check. No. And let's figure out what's going on. That was okay. Control P, control.
2,000 years later.
All right, so I know there's something wrong, and it's funny. My eyesight are not good, but here's the problem. The outflow, 1.5 gallons per second. That's huge. That's humongous. And that was the problem. It's 1.5 gallons per minute. So the unit, I picked the wrong unit. So we gotta go back, input data, units, and what was that? Maybe loads on motion, flow rate, and volume flow rate. Here we go. It's gallons per minute. There we go. Gallons per minute. We say okay. And now we go back and check this. The volume flow rate now. I got it changed that to 90 gallons per minute. Gotta go back and put the right number there. And the right number is 1.5 gallons per minute. No wonder the pressure were all over. It was weird. There we go. Then I think Let's double check again. Yeah, and this internal pressure 40 pound or 40 psi. Now it looks good. So everything looks good. So now it makes a lot of sense. Now, what else I need to do? Let's run this. Run. Like to run it the other way around, like this. And now we go back here and check what's going on quickly here with my numbers. Good. Now the pressure is going up. It should be the way it should be. Excellent. It's just moving to the probably to the inlet pressure. Now, how about with this? Let's check on that plane. Now that should be, I don't know, 15 millimeters. Plane offset from what plane? XY. Let's see. There we go. Now we're talking. See how this is moving? Because that's part of the rotating body. And right now the pressure is somewhere here. And I got a blue pressure. Let's see. And the torque. Is negative. And dropping. And the pressure, the outlet pressure, pretty much the inlet pressure. It's about 40 in the inlet, so 39 at the outlet. Now let's see where we are. This is not this. I set this to 1 second so you can see how fast it's moving. It's gonna take a while. Now you can see the green, pretty much the pressure here is pretty much all this on here. It's about 40, but on the blue it's a little bit lower here at the exit, which is about, I don't know, somewhere here between around 39.8. So the pressure drop no more than perhaps 0.2 psi on this tiny turbine. So it's gonna take a while. I mean, we are gonna do this for about a second. So, and it's moving very slow because I have a step size about 0.002, I believe. That was a step size for this. So, see high pressure here, how it builds high pressure, very low pressure now here, because this pretty much in that the rotation is pretty much taking all the pressure from this part. So these tend to move due to the differential pressure. But the pressure drops not more than 40 here, 38.8 here. That means 0.2 psi. You multiply that by the flow, 1.5 gallons per minute. That will give you an idea of what the potential watts that this item will generate under these conditions. If it allowed to rotate about 50 RPMs. So you are extracting good amount of energy probably out of, yeah, or whatever energy can be extracted from this. Don't expect much. So let's see, let's go back again to our what's going on here. On the green, it's kind of fluctuating, but it's dropping 0.007. You will say that's a very tiny number. It is, because it's a tiny turbine. And my expectation that this shouldn't be higher than 0.002 or 0.003 negative, meaning that is turning, I mean, you are extracting power out of it. So what we're gonna do now is, when this is done, we'll be back and get you the final results out of all this.
2,000 years later.
All right, so pretty much the solver finished, but obviously on time. You can see the kind of the torque went from a minimum to a maximum. So the average value is negative 0.014. And let's see what else we got here. Let's see, keep fluctuating up and down, up and down. And this is where I pretty much finish with on time. Let's see what else we have here. Maximum of 1 seconds. And now let's take a look to this result, particularly through trajectories, and let's insert that, and let's see how this looks like. It's gonna be, in this particular case, it's gonna be, let's see, let's use this part here. Let's take a look here from this inlet up to here, and edges clear selection. It's not edge, but I want face. Let's see if I can get the face. There we go. That internal face and this internal face. And now let's increase this, I don't know, 100 lines, and lines arrow, that will do. Pressure, actually speed, velocity, and let's generate that. See how this looks like. There we go. On the high speed, kind of this color here somewhere, getting in, and now the flow coming out, and some of the flow bypassing on the back of my friend here, the turbine. And I don't know, it looks kind of good. Let's do it again. Let's see. Let's do animation on this. I don't know, not much I can add there. Good enough there. So let's stop this and let's look into cut plot, and let's see, insert, and let's take a look where that will be. Let's look in the front plane, but it's right in the middle. This box here is right at the middle, and that will be okay. That it's come up like will work okay. That's 0.02. So, and contour, yep, contour. Anything else that will be on velocity? How about pressure? Let's see pressure, and let's apply on that one, and let's see. Now I can pressure on the brown. It's about 40. Getting in, you can see a red here right when this perhaps touch that up, and on the green coming out, the pressure here is lower than that, the pressure in the getting in. Now let's see, let's do what we're gonna do on this one, let's do on the cut plot. So we say play, but on the bottom up, let's see, you can see how it's moving. To the pipe, there we go. I mean, not much. I guess that the numbers are the ones coming from, you want to make numbers, entertain numbers, they are the ones coming from here, from the goal plot. So we insert that. Actually, let me stop this, the card plot. Remove that for a second. Let me hide that, and let me go into goal plot, insert, and it's gonna be all, but then I'm gonna show, so they're right here. So these are the numbers. See, the torque is negative 0.014, and that's Newton meters. Look like on the high side. Need to check on those numbers. Need to entertain this number here, negative 0.014, and let's see, the RPM was about 50 RPM. So let's do this. Let's do the math, and I'm gonna prepare an Excel table with these results, so you can see how this looks like. I'll be back. All right, just to finish everything here on this video, this is the story. The outlet pressure, the average outlet pressure was 39.81. Remember that the inlet pressure was 40, so that will give you a pressure drop of 40 minus this value. That's the pressure drop. Now, in theory, the maximum watt capacity that you can recover from this turbine can be calculated by all this number here. I'm going to explain you very quickly. For example, the pressure drop, now the unit there are pound per square inch, so you got to multiply by 144 so that they become pounds per square foot, but then you need to multiply, that's the flow rate. Remember, the flow rate was 1.5, but that's gallons per minute. So those gallons per minute you divide by 7.48, so that becomes cubic feet. And then the minute you divide by 60, so now you have in second. Now, the 550 come to convert all this number up to the 550. That would be horsepower. That would be a tiny number. So then you multiply by 746 and you convert that in watts. So that's the total watt capacity that can be extracted from the pressure drop. Is about 0.12 watt. That's very, very small. Now, if you want to concern, can you light a LED? Let's say a 3-volt LED. So a 3-volt LED, let's say that those are the watts. If you divide that by 3 volts, that divided by 3 volts, that's the amount of amp that you can extract. That would be, multiply that by 1,000. So definitely a LED will be light up pretty nicely, because this will be milliamps. So yes, a 3-volt lamp will light pretty nice, because at 41 milliamps it will glow good, but very tiny, 0.12 watts. I mean, that's maximum. That's just based on pressure drop, based on the calculation done by torque calculation as per your flow simulation and all that. The torque was about, when it stopped right here, 0.14. That's Newton meters, and shown here at the RPM that I was working at 50 RPMs. That will give us, if you multiply this to number and then you convert this number to rad per second, which is based on here. Let's pop that up. So you see the 2 pi divided by 60. That's to convert this number, the RPM to proper rad per second. The whole thing will give you watts, which is what you want, Newton meter over second. That's the definition. Newton meter is joule, joule by second, that's watts. So that's actually the energy that you're extracting at 50 RPM. Not much. I mean, almost half of the whatever was there to start with. But that's give you that the turbine efficiency is about 59%. And that's basically it. That's the the end of this story. And so through, we're gonna close here. And anything else that I need to do here? No, that's basically it. So that's the the design of this turbine. And I did this turbine for I'm gonna do a 3D printing of something similar to this turbine, and and test this theory of flow simulation. Let's see how well it's gonna adhere to the calculation versus the experimental results. So again, I'm gonna be testing a little bit more the mesh, because the local mesh, as you remember, I might increase it a little bit more, like 3 here and 3 here, but that take forever. It took about half an hour to get this done from when I stop and I start back again. I'm doing this in a laptop, kind of slow, but I don't know, maybe I will increase this and find out whether it can get better. Not sure, but that's part of the thing that you need to do. And the other one is perhaps increase this globe of mesh as well. Right now it's on 3, maybe I need to increase it to 4 or 5 for and see how much variation I get on the numbers. That's basically it. I hope you like it, guys, and I goof it up a couple of times here and there, but I leave all those mistakes so that you learn from them. And as always, I said, have a great day. Bye.